The chip industry is the foundation of nearly every industry. Chip manufacturing demands extreme precision, producing features 1,000 times smaller than a bacterium, and on the order of a single gold atom or a strand of human DNA. Lithography, the process of creating patterns on a wafer, is the beginning of the chip manufacturing process and consists of two stages: photomask making and pattern projection. It is fundamentally an imaging problem at the limits of physics. The photomask is like a stencil of a chip. Light is blocked or passed through the mask to the wafer to create the pattern. The light is produced by the ASML EUV Extreme Ultraviolet Lithography System. Each system is more than $250 million. ASML EUV uses a radical way to create light: laser pulses firing 50,000 times a second at a drop of tin, vaporizing it, creating a plasma that emits 13.5 nanometer EUV light, nearly X-ray. Multi-layer mirrors guide the light to the mask. The multi-layer reflectors in the mask reticle take advantage of interference patterns of the 13.5 nanometer light to create finer features down to 3 nanometers. Magic. The wafer is positioned within 1/4 of a nanometer and aligned 20,000 times a second to adjust for any vibration. The step before lithography is equally miraculous. Computational lithography applies inverse physics algorithms to predict the patterns on the mask that will produce the final patterns on the wafer. In fact, the patterns on the mask do not resemble the final features at all. Computational lithography simulates Maxwell's equations of the behavior of the light passing through optics and interacting with photoresists. Computational lithography is the largest computation workload in chip design and manufacturing, consuming tens of billions of CPU hours annually. Massive data centers run 24/7 to create reticles used in lithography systems. These data centers are part of the nearly $200 billion annual CapEx invested by chip manufacturers. Computational lithography is growing fast as algorithm complexity increases, enabling the industry to go to 2 nanometers and beyond. Nvidia today is announcing Culitho, a library for computational lithography. Culitho, a massive body of work that has taken nearly 4 years, and with close collaboration with TSMC, ASML, and Synopsys, accelerates computational lithography by over 40 times. There are 89 reticles for the Nvidia H100. Running on CPUs, a single reticle currently takes 2 weeks to process. Culitho, running on GPUs, can process a reticle in a single 8-hour shift. TSMC can reduce their 40,000 CPU servers used for computational lithography by accelerating with Culitho on just 500 DGX H100 systems, reducing power from 35 megawatts to just 5 megawatts. With Culitho, TSMC can reduce prototype cycle time, increase throughput, and reduce the carbon footprint of their manufacturing, and prepare for 2 nanometer and beyond. TSMC will be qualifying Culitho for production starting in June. Every industry needs to accelerate every workload so that we can reclaim power and do more with less. Over the past 10 years, cloud computing has grown 20% annually into a massive $1 trillion industry. Some 30 million CPU servers do the majority of the processing. There are challenges on the horizon. As Moore's Law ends, increasing CPU performance comes with increased power. And the mandate to decrease carbon emissions is fundamentally at odds with the need to increase data centers. Cloud computing growth is power limited. First and foremost, data centers must accelerate every workload. Acceleration will reclaim power. The energy saved can fuel new growth. Whatever is not accelerated will be processed on CPUs. The CPU design point for accelerated cloud data centers differs fundamentally from the past. In AI and cloud services, accelerated computing offloads parallelizable workloads, and CPUs process other workloads like WebRPC and database queries. We designed the Grace CPU for an AI and cloud-first world, where AI workloads are GPU accelerated, and Grace excels at single-threaded execution and memory processing. It's not just about the CPU chip. Data center operators optimize for throughput and total cost of ownership of the entire data center. We designed Grace for high energy efficiency at cloud data center scale. Grace comprises 72 ARM cores, connected by a super high-speed on-chip scalable coherent fabric that delivers 3.2 terabytes per second of cross-sectional bandwidth. Grace Superchip connects 144 cores between two CPU dies over a 900 gigabytes per second, low-power, chip-to-chip coherent interface. The memory system is LPDDR, low-power memory, like used in cell phones, that we specially enhanced for use in data centers. It delivers 1 terabytes per second, 2.5 times the bandwidth of today's systems at 1/8 the power. The entire 144-core Grace Superchip module with 1 terabyte of memory is only 5 by 8 inches. It is so low power, it can be air-cooled. This is the computing module with passive cooling. 2 Grace Superchip computers can fit in a single 1U air-cooled server. Grace's performance and power efficiency are excellent for cloud and scientific computing applications. We tested Grace on a popular Google benchmark, which tests how quickly cloud microservices communicate, and HighBench Suite that tests Apache Spark memory-intensive data processing. These kinds of workloads are foundational for cloud data centers. At microservices, Grace is 1.3 times faster than the average of the newest generation x86 CPUs, and 1.2 times faster at data processing. And that higher performance is achieved using only 60% of the power measured at the full server node. CSPs can outfit a power-limited data center with 1.7 times more Grace servers, each delivering 25% higher throughput.